Hey there, today we're going to talk electric fields, electric potential, also known as voltage, and a bit about some devices called capacitors. I mentioned earlier that electricity and gravity are really similar, to the point that their fields are also really similar. So if I've got the Earth, and somewhere out here, in the middle of space, there is nothing, then there should be no force there, no object with mass, no means to feel a gravitational force. Remember, mass is just how things interact with a gravitational field. But I know if there was something here, it would feel a force toward the center of Earth. And that's the purpose of gravitational fields, to tell us what direction things with mass would feel a force in a certain region of space, and what the magnitude of that force would be. It would basically tell me how many newtons of force would I feel for every kilogram of mass I put at that location. And so I can find the strength of the gravitational field as just the gravitational force divided by a mass, where m is a small little test mass. Imagine I'm putting this tiny little object at different points in space. It doesn't matter what the mass actually is in kilograms, because I'm dividing it out. We know that the force between any two objects with mass is gm1 m2 over r squared. So if I divide out that little test mass from this equation, I end up with the gravitational field due to Earth being big G, that's 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared, times the mass of Earth, so this is the central mass, whatever is creating the field, and r is just the distance away from the object where you're going to be measuring the field. That's going to be in meters. Okay, so I end up with an answer in newtons per kilogram, and that's fine. That tells me if I put 1 kilogram of mass here, this many newtons is what I get. If I put 2 kilograms of mass here, I get twice that amount of force in newtons. So it's pretty much just a shortcut to figure these sorts of things out. Well, electric fields are really similar, except they describe what a positive test charge is. And this is just convention. Scientists were like, well, it's not as easy with a mass, with gravity, because with a mass, all I can do is either have mass or don't. With charges, you could have a positive charge or a negative charge, so they landed on positive. So electric fields, as a result, point toward negative charges, because positives are attracted to negatives, and they point away from positive charges. And just like the gravitational field, I can solve for it by taking the electrostatic force, because remember, the way to interact with the electrostatic force is to have a net charge, Q. So I can take that force, divide out some test charge, kind of like my tiny little test mass that I was holding in space around Earth, and I get what's called the electric field strength, denoted by E. So if you start with Coulomb's law, that the electric force is kq1 q2 over r squared, and divide out one of those test charges, then I end up with an electric field just being K, which is, again, Coulomb's constant, 9 times 10 to the 9th. Q is just the charge of the object creating the electric field, and R is the distance away from that charge that you want to measure the electric field strength. When all is said and done, you'll find an electric field in units of newtons per coulomb. So newtons per coulomb. So again, that's basically just telling me if I were to place a charge here, a 1 coulomb charge, how many newtons of force would I get out of it? And then I can extrapolate out and decide for any number of coulombs of charge how much force I'm going to get out of it. It's kind of a shortcut that way. Oh yeah. Now, a couple of quick distinctions. Electric field lines are not necessarily the path that the electron is, or proton, or whatever the charged particle is going to follow. In fact, it's usually not. It's just the direction at that point in space, exactly the way it's going to be feeling a force. So here are a few examples. If you have a positive and negative charge, the lines go away from positive and toward negative. And notice how in the middle, all the lines are perfectly horizontal. Here's why that is. If I imagine the electric field just from the positive charge, it points away. If I imagine the electric field just from the negative charge, it points toward it. In this case, when I break my electric field vector into x and y components, my y components are actually canceling with each other, one up and one down. But both my x components are pointing to the left, so I end up with an electric field at this point in space just pointing to the left. So electric field, just like all other vectors, find the electric field due to one charge, find the electric field due to the other, and then treat it like you would any other vector. Figure out whatever angles you need, break it into x and y components, and add them up that way. If I have two negative charges, it looks just like the gravitational field would of two objects with mass. In the center, there's no field. Well, the field strength is 0, simply because I would feel equally attracted both ways. And for two positive charges, it's a really similar shape, but all the lines are pointing away because positives repel from positives. If you got lines of charge, you end up actually with straight lines between it. So I'd have one plate, let's say positive Q, one plate negative Q, and these lines of charge connecting it this way. And I included a ring of charge picture just because I thought it looked cool. So as you sketch these field lines only start on positive charges, they only end on negative charges, always and forever. The number of lines, and this is kind of technical, if I've got a really strong positive charge, a fairly weak negative charge, I'd have more lines coming out of the positive than I do have going into the negative. I'm not going to count your lines on each and every example, but this is how it's done if you want to be absolutely precise about it. Field lines never cross because I can never feel a total net force in two directions at one time. And again, E fields are vectors, so the field direction with multiple charges, like I said last slide, can be found with vector addition. Well, let's talk a bit about gravitational potential energy. I know that the work done is a change in my potential energy, and it's going to be equal to the force times change in distance. If I look at it in terms of calculus, if I take a small little sliver of increase or decrease of potential energy, that will come from a small little sliver of change in distance from the center of Earth. If I integrate both of those, I end up with, boom, the universal potential energy for gravity. Now, the only reason I'm showing you this, I'm not really going to test you on this equation, is, the equation, of course, being U equals negative G m1 m2 over R. But I'm not really going to test you on that. Instead, I'm going to test you on electric potential energy. The electric potential energy looks a lot like Coulomb's law, except the equation is simply K Q1 Q2 over R, not over R squared. One other difference is that this is a scalar, not a vector. So, the negative of any Q can't be ignored. If you remember when I talked forces, and same goes for fields, I suggest you ignore any negative that you'd get out of Coulomb's law. Just plug in the magnitude, the absolute magnitude of these charges, and solve for the direction of the force yourself. That's not the case for energy. Because energy is a scalar, negative doesn't mean anything in terms of direction because there is no direction for it. It just means the raw value. So if I have one positive and one negative Q, I will actually get a negative potential energy in joules. Now, voltage is kind of like the electric field equivalent of energy. And what I mean by that is, imagine taking a tiny little test charge, holding it out into some empty region of space, and figuring out exactly how many joules of potential energy you're going to have there. So it's pretty similar, and you end up with joules per coulomb. So again, if I've got a charge just somewhere out in space, and some distance r away from it, there's nothing there, but I want to know how many joules of energy I could get for every coulomb that I place at that location. That's what a volt is. A volt of voltage. Nice. So, if it's the potential energy is K times Q1 times Q2 over R, and I'm dividing out one of those Q's, voltage is just K times Q, where Q is whatever's creating the voltage that I care about, divided by R, where R is the distance away from that charge you are in space, where you want to measure that voltage. Another nice thing about it, again, just like energy, voltage is a scalar. It means you can't ignore any negatives, but it makes it a lot nicer for solving problems. You don't have to worry about any angles. You don't have to worry about breaking anything into x and y components because there are no x and y components of scalars. All you got to do is some simple addition. So let's say I've got a point in space and I want to know the voltage there. If I have, let's say, 3 positive charges and 2 negative charges around it, all labeled Q1 through Q5, and I know the distance that each and every one of these particles is from point P, then I can find the voltage contribution from each and every one of these charges. Just K times Q divided by R, where R is the distance from point P, and Q is the charge on that object that's causing the voltage. So I'd have V1 equals K Q1 over R1, and the same for all the rest. Now notice that the negative charges are going to give you a negative voltage, because Q is a negative number. Right? But that's okay. So you get a value for V1, V2, V3, V4, V5. Your final voltage is just going to be a combination of all of them. Some numbers positive, some numbers negative, doesn't matter. So however many charges you have, find the voltage contribution from each one individually, and then just straight up add them. Nice. Now, there are several names for voltage. You might find it as just voltage. You may find it as electric potential. And you may find it as potential difference. The real reason, which I'm not going to get too far into, is about how the zero voltage universally is found at an infinite distance away, which is kind of mind-blowing. But what really matters is a difference in voltage. Kind of think of it like this. Voltage by itself is pretty insignificant, and you can think about it in terms of potential energy. I can be at a really, really, really high potential energy, right, way up on a ledge, and if I take a step, then okay. If I step onto another region with the same high potential energy, I'm totally fine. That's just me walking on a really high up platform. When there's a difference in potential energy, so I've got a high potential energy and then I step off to open air just above the ground, that's when things start to get interesting. And the same thing happens with electricity. So I can be at a crazy high voltage. I can be at 1,000,000 volts and feel not a thing, until there's a connection from me at 1,000,000 volts down to some like 0 volt potential. With voltages, you're going to find stuff that look a lot like topographic maps. Topographic maps show lines of regions that are at the same elevation. Now, from fall semester physics, you remember elevation is just another fancy way of talking about potential energy. Everything along this line has the same gravitational potential energy. Equipotential lines are the same, except for voltage. There's no direction. There's no, again, since voltage is a scalar, that's about it. And there are several examples when you have several different types of charges around. You should find for a dipole, which is one positive charge, one negative charge, you get that crazy little spider pattern of electric field. And the rings of equipotential seem to squish together toward the center. You actually are going to find a 0 voltage right in the middle. For a capacitor, which are a couple of different lines of charges, one positive, one negative, the electric field lines are actually straight across, with the equipotential lines being at 90 degrees to them, vertically at all points. Speaking of capacitors, again, these are oppositely charged plates. You got an insulating material between them. The purpose of it is to store electrical energy. It can charge up energy and it can discharge it. One of the favorite examples I like to use are those old disposable cameras with those loadable flashes. If anybody remembers those, you hit a button and you kind of hear I hope that came across all right in this iPad video. But that's just the sound of a capacitor inside loading. The battery isn't able on its own to give out enough energy all at once to make the flash work, so you use a capacitor for it. Capacitance is just the ratio of the amount of charge you're going to build up on each plate versus the change in voltage between them. So you end up with an equation Q equals C delta V, where Q is the magnitude of charge on each plate. One is positive and one is negative. And delta V is the change in voltage that you ultimately go through if you travel from one plate to another. And C is just going to be the ratio between them. So C equals Q divided by delta V, the ratio of charge per voltage that I'll get out of those different charges. And the unit of capacitance is just a coulomb per volt, which just means a farad. Oh, some practical applications. Every single RAM chip in a computer has a ton of capacitors, millions of them. Some that are charged up read 1, some that are discharged read 0. And hey, you got binary. Defibrillators, super important. They're just large capacitors, and the human body becomes the connection between those two plates. And lightning's kind of a natural example of a capacitor. When you have a layer of cloud and a layer of ground, cloud, ground, and they build up different charges, well, that, folks, is a capacitor. And if it builds up enough, you'll get a discharge of that capacitor. That's lightning. Finally, I mentioned that energy is kind of the whole purpose behind capacitors, so I can solve for the energy in joules as U equals 1/2 times Q, the charge, times delta V, change in velocity change in voltage between these plates. All right. I think that's enough for now. I will see you all in class, and have a great day.